This winter might be colder than any previous winter. The World Meteorological Center has just issued a warning. There's a very high probability of a La Nina event this year. Do you remember that bitter blizzard of 2008? Back then, many regions across the country were caught off guard by the drop in temperatures. During the spring festival travel rush, tens of thousands were stranded in Guangzhou. Train and flight services were widely suspended. Friends in the south even saw for the first time cities frozen over with high-voltage power lines. And this year might be even colder. So, what exactly is the La Nina phenomenon? It occurs when the seawater near the equator in the Pacific becomes unusually cold. It alters global atmospheric circulation, allowing cold air to push further south. Simply put, it makes it harder for cold air to move. If it continues to intensify, it could easily lead to frequent cold waves. Not only will winters be colder, but the rain and snow will hit more fiercely. Meteorological experts predict that if the La Nina phenomenon persists this winter, cold air will sweep south from the Mongolian plateau, first impacting the Beijing-Tianjin-Hebei region, then crossing the Yellow River and the Yangtze River, and finally reaching Guangdong and Guangxi. In other words, winters in the south will be colder than ever before. By the way, Earth's cold air is actually stored up. The planet's largest cold storage is in the Arctic and Siberia, where winters have little sunshine. Heat dissipates quickly there. Cold air accumulates over time, just like a storage room that gets fuller and fuller. Once the air pressure builds high enough, the cold air bursts out in clusters, rushing directly from high to mid-latitude regions. Cold air doesn't just drift south. It doesn't wander aimlessly. It travels along a high-speed highway, which is the jet stream high up in the sky. Normally, the jet stream acts like a lock, keeping the cold air confined to the north. But if something goes wrong with the jet stream, and its direction changes, the cold air can follow the curve and surge south, delivering the cold right over our heads. The key phrase this year is La Nina, the cooling of the Pacific waters. This will change global atmospheric circulation, making the East Asian winter monsoon stronger, and giving the cold air more strength. Simply put, it's like installing a booster for the cold air. It arrives faster, strikes more forcefully, and lingers longer. Above the Arctic, there's an atmospheric cold dome called the polar vortex. Normally, it keeps the cold air locked in tight, but once this dome loosens, the cold air escapes rapidly, rushing into the mid-latitudes, dropping temperatures below freezing overnight. Every time there's a sudden drop during a cold wave, the polar vortex is usually to blame. As the area of snow and ice expands, the Earth seems to don a white, reflective coat, sending sunlight back into space. With less sunlight reaching the surface, the ground grows even colder, and at night, heat escapes more quickly. The next morning, temperatures drop even further. This is the vicious cycle of cold upon cold. Beyond short-term factors, the Earth's temperature is also influenced by solar activity. When sunspots are abundant, the Earth warms up a bit. But when sunspots are scarce, the Earth tends to grow colder. Moreover, the Earth's orbit is not perfectly round. It deforms every few tens of thousands of years, and its axis wobbles. These cycles determine when an ice age will occur, although they don't directly affect this year. They constantly impact the Earth's climate. Don't assume that global warming means it won't get colder. In fact, warming causes Arctic ice to melt faster, making the jet stream more prone to shifting, which increases the chances for cold air to break free. Coupled with the moisture from warmer oceans, even blizzards could become more severe. In other words, future cold could be even more extreme. Usually our summers are warm, but winters can be even harsher. There was a time when Earth became so cold that it turned into a frozen planet. Scientists have found ample evidence all over the world. For example, glacial striations on rocks in low latitudes. On the ocean floor, dropstones carved by ice can be found in the mud. And in some cases, a layer of carbonate rock covers glacial deposits. Combined with paleogeographic analysis, they discovered that these glaciers once appeared near the equator. For instance, during the Huronian glaciation 2.1 billion years ago, the sun above Earth was still very young. Its brightness lower than today, marking the Earth's first great freeze. Another example is the Marinoan glaciation 635 million years ago, when Earth was almost entirely covered by ice sheets for millions of years. Even the equatorial oceans froze over. During that icebound period, it was an extremely quiet world, with thick ice layers covering the ocean surfaces, and only a few cracks and open waters available. The atmosphere was extremely dry and cold. Chilly winds swept across the sky, mixed with dust, casting a perpetual gloom over the surface. Yet life still existed during this period, as sunlight penetrated the clear ice, giving cyanobacteria beneath a chance to photosynthesize. So after Earth was frozen for so long, how did it eventually thaw? The answer lies in Earth's internal volcanoes, which were not located on the surface, and thus not affected by the cold. During the millions of years when the planet was locked in ice, volcanoes continuously released carbon dioxide into the atmosphere. Because surface weathering nearly stopped, the atmospheric CO2 gradually accumulated, intensifying the greenhouse effect, which eventually broke Earth's icebound state in one fell swoop. Initially, the sea ice near the equator began to melt, allowing the surface waters to slowly absorb heat, and the melting gradually accelerated, as volcanic activity caused global temperatures to soar rapidly, triggering a super greenhouse effect, while torrential rains and acid rains swept over the continents. A massive layer of carbonate rock was rapidly deposited in the oceans, which is what we now see as cap carbonates. During the billions of years that Earth was frozen, life did not freeze to death. In fact, it may have even driven evolution, with microorganisms in the ice learning to eke out an existence under extreme conditions. After thawing, nutrient pulses flooded into the oceans, and oxygen levels rose. Soon after, complex ecosystems emerged, with multicellular life beginning to dominate the seas, ushering in the Cambrian explosion. In other words, Earth's extreme cold once served as a catalyst for life. So, here is the question. Will Earth turn into an ice ball again in the future? From an astronomical perspective, the next major ice age may not arrive for thousands of years, while modern humans are emitting vast amounts of greenhouse gases, with rising CO2 levels pushing Earth toward warming. So, in the short term, we won't see a return to a frozen planet. But scientists caution that Earth's climate has tipping points, and once a threshold is crossed, changes won't be gradual, but rather catastrophic. So, whenever we experience extreme weather, blizzards or cold snaps, we are reminded that Earth can suddenly flip, and do so quite thoroughly. Although Earth may occasionally enter ice ages, when compared to the frozen planets in our solar system, Earth's chill is nothing special. Today, let's look at 3 true cold kings of the universe. Europa, Jupiter's frozen moon, Triton, Neptune's rogue satellite, and a super cold planet hidden deep in the galaxy. First stop, Europa. It is called the ocean world beneath the ice. Europa is a moon of Jupiter, slightly smaller than Earth's moon. Its surface is covered with thick ice. From space, it appears full of cracks and stripes. These cracks aren't just decoration. They are caused by Jupiter's massive gravity constantly pulling Europa, stretching its surface, generating heat inside it. Scientists speculate there might be a global ocean tens of kilometers deep beneath the ice, containing twice as much water as all Earth's oceans combined. Although surface temperatures usually range from minus 160 to minus 220 degrees Celsius. Sunlight is almost useless here, but tidal heating acts like a heater, preventing all the sea ice from freezing solid. If humans could one day drill through the ice shell, they might see a dark world full of potential for life. There could be underwater volcanoes like Earth's deep-sea hydrothermal vents, erupting hot fluids, providing energy for microbes. This is why Europa is considered the most likely place to find extraterrestrial life. The second stop is Triton in the solar system. Triton is Neptune's largest moon, but it orbits Neptune in a retrograde direction. This suggests it might not be Neptune's original moon, but a foreign object from the Kuiper Belt, later captured by Neptune's gravity. Triton is colder than Europa, with surface temperatures around minus 235 degrees Celsius, one of the coldest places in the solar system. Its surface is covered with nitrogen and methane ices. Even black stripes appear, traces left by erupting nitrogen gas geysers on the surface. Even more amazingly, it may have cryovolcanoes, indicating Triton is geologically active and not completely dead. Not a fully lifeless planet. The third stop is outside the solar system. This is the host planet from deep in the galaxy. Scientists discovered a planet called OEGU 2005 BLG 390LB using gravitational microlensing. It orbits a dim red infrared star with temperatures consistently around minus 220 degrees Celsius, even colder than Triton. Its surface might be a thick shell of high-pressure ice, several kilometers thick, like a huge icy iron ball. But scientists speculate radioactive decay inside could produce heat, supporting a dark ocean under high pressure, where there is no sunlight, but possibly microbes surviving on chemical reactions. This world, tens of thousands of light years away, is like an isolated island deep in the galaxy, silently drifting in the darkness. It reminds us, the universe may be full of such cold, quiet worlds. Their surfaces are lifeless, but they may hide answers to life beneath. We often think life needs sunlight, but Earth has long proven otherwise. Life exists at deep-sea hydrothermal vents under Antarctic ice and kilometers beneath the crust. These worlds might be the cosmic life vaults. Their surface is as cold as absolute zero, but with turbulent currents inside. Life might not need sunlight, just energy and some liquid water to quietly thrive in these icy worlds.